Okay, what I wanted to bring together now is the idea of the standard error, confidence intervals and hypothesis testing. Before I do that, I just want to recap on a few sort of crucial elements that we've covered before. So the first is that there's certain measures that we use as a indicator of a central tendency, and one of those is the mean. We also have a measure which gives us an idea of the variance within a population, or more usually the variance within a sample, and we call that the standard deviation. And we've previously covered how to calculate the standard deviation, and we've also covered how to calculate the mean. What we've also discussed is that on a normal distribution, for a frequency distribution, so a normal distribution of x, the mean will be in that central area, as will the mode and the median. The mean will be there, and the values within that distribution, 95% of them will be within approximately 2 standard deviations of the mean. I say approximately because the exact value is 1.96 standard deviations. So 1.96 standard deviations. So within that range, we would expect 95% of our values. Okay, so we just need to make sure that bit's clear. What I'm going to talk about now is the standard error, and I'm going to link that with confidence intervals and hypothesis testing. So standard error. In order to do that, we have to get our heads around a particular theory called the central limit theory. Central limit theory. Central limit theorem. So I just want to explain that first. The central limit theorem, what that says is that if we have a population, and we'll illustrate a population with a frequency distribution. So our population might be a skewed population, like that, or it might be a normal distribution, like that. And in each case it's going to have a population mean, and we usually denote that like that. Now, what the central limit theorem says is if we take a sample from our population, it doesn't matter if the population is the skewed one or the normally distributed one, but if we take a sample from that, so we'll call our sample size n, and if we work out a mean from that sample, which is pretty straightforward, and if we then start plotting, if we then plot that mean onto another frequency distribution, and then repeat that, so we take another sample, calculate a mean again, plot it again, and then repeat and repeat and repeat, then as long as our value of n, the size of our sample is big enough, as long as the size of the sample is big enough, we will get a normal distribution. And because it's a normal distribution, it will have certain characteristics. One of the characteristics will be that the mean of all those sample means, because we took loads of sample means, and we can calculate a mean of all those sample means, is going to sit there, isn't it, in that middle bit. What the central limit theorem tells us as well, which is very useful, is that that mean of the sample means, if we've taken enough samples, is actually equal to the population mean. It also tells us it doesn't matter whether your population is skewed or a normal distribution, as long as your size of n is big enough, then you're going to get a normal distribution. So because it's a normal distribution, the other thing is that we know where 95% of our values are going to lie, don't we? Because it's a normal distribution, so therefore 95% of our values will lie within either minus 1.96 standard deviations or plus 1.96 standard deviations from the mean, because that's a characteristic of a normal distribution. So 95% of any sample, if we calculate the mean from that population, it will lie within 1.96 standard deviations of the mean, which means that 5% won't. 5% will be outside that range. Now, in this context, when we talk about the standard deviation, we use a different terminology. We're talking about here the standard deviation of the sample mean, and what we actually call that is the standard error of the sample mean. So the standard error of the sample mean. So it's a standard deviation, but it has a different terminology. Standard error of the sample mean. Okay, so just to recap a little bit with that, we're saying that for any sample from this population, what we've done is repeatedly taken samples, we've worked out the mean, and we've plotted them, and we get this distribution, which is a normal distribution. And because of the characteristics of the normal distribution, that means that we can say that 95% of any of our mean samples will fall within 2 standard errors from the population mean, or the mean sample mean, or the population mean, because they're both the same. Yeah. So just to denote that, what we're saying is that for any sample mean from that population, that's going to fall within a range of our population mean plus or minus 1.96 times the standard error of the sample mean. And if we flip that around just using simple algebra, we also know therefore that our population mean is going to be equal to our sample mean, any sample mean that we might take, 95% of the time that is. So 95% of the time, our population mean is going to be equal to the sample mean plus or minus 1.96 times the standard error of the sample mean. And suddenly that's really useful, because it's giving us a value within which our population mean is likely to be. So we're using our sample mean, we're taking a sample, we're calculating a mean, and from that one sample, we're then forming a range within which we can say, in this instance, we're 95% sure that our population mean is going to lie within that range. Might not do, there's a 5% chance it won't do, there's a 95% chance it will. And with that, so like I said, we can calculate our sample mean easily. We know how to do that. We just add up the numbers in our sample and divide by the we add up the values in our sample and divide by the total number in the sample. But can we calculate this bit, the standard error of the mean? And yes we can. And the way we do that is by using this equation. So the standard error of the mean is equal to the standard deviation of our population divided by the square root of n. So what we're saying is that our standard error is inversely proportional to the size of our sample. So as the size of our sample goes up, this bit here, this bit will reduce in size, and therefore the range within which we're saying our population mean falls within gets narrower. Yeah. So the smaller our standard error is, the more precise our estimate is of the population mean. The problem is we don't know what the standard deviation of the population is. The population will be too big to ever work that out. That doesn't matter, because as long as our sample is sufficiently big, then the standard deviation of our sample is going to approximate to that. It's going to be pretty close to that. So therefore, our standard error of the sample mean, we say, is the standard deviation of our sample divided by the number in our sample. And this is the basis of confidence intervals. What we've calculated here, when we put this bit into there, which we can easily do, we can calculate all of that, and we're going to have a confidence interval